Hello my friends and welcome back to the You Can Do TV channel. At the Akangaran pipe and metallurgical plant in Uzbekistan, a new chapter in industrial capability begins with the launch of the high-technology hot rolling mill 550. This fully automated line transforms continuously cast steel billets into precision hot-rolled strip through a tightly controlled thermal and mechanical process. Billets are reheated to exact rolling temperatures, then passed sequentially through roughing and finishing stands, where thickness and width are reduced with millimeter accuracy. The mill produces strip ranging from 165 to 440 millimeters in width and 1.2 to 6 millimeters in thickness, with a production capacity of up to 30,000 tons per month. Advanced automation systems regulate rolling force, speed, and temperature, ensuring consistent metallurgical properties and surface quality. The output feeds directly into an integrated pipe welding complex, where the strip is longitudinally slit and formed into electric resistance welded pipes and profiles. This closed production cycle, from continuous casting to hot rolling and pipe welding, delivers clear value, reduced import dependence, stable quality, and high volume efficiency. The mill supports construction, heavy industry, machinery manufacturing, and infrastructure projects. More than a production upgrade, Mill 550 represents a strategic investment in domestic industrial strength, technical self-reliance, and long-term economic growth. Behind every heavy-duty wind turbine, steel mill, or offshore platform, there is a hidden mechanical heart, gigantic gears manufactured with almost microscopic precision. The machining of large-scale bevel gears represents one of the most demanding disciplines in modern mechanical engineering, where mass, metallurgy, and microns must coexist without compromise. This process combines the latest CNC technology, advanced heat treatment, and closed-loop quality control to deliver components capable of transmitting enormous torque over decades of service. The journey begins with integrated CNC turning and gear cutting, designed to ensure absolute geometric consistency from the first operation. Semi-finishing is carried out on high-performance CNC gear cutting systems, including the world's largest face-hobbing C300 machine. At this stage, the gear blank is transformed into a defined tooth geometry using a universal up gear cutter with a diameter of 160 millimeters. The gear in focus features a module of 11.667, 54 teeth, a 20-degree pressure angle, and a mean spiral angle of 35 degrees right hand. With an outside diameter of 633 millimeters and a face width of 118 millimeters, the component already reveals its massive scale. The selected material, 18CR Nemo 7-6, is a high-performance case-hardening steel chosen for its exceptional fatigue strength and core toughness. During semi-finishing, cutting paths are carefully optimized to balance productivity with tool life, while CNC systems continuously monitor load, vibration, and thermal behavior. This ensures dimensional stability long before final geometry is achieved. Once the basic tooth form is generated, attention shifts to edge quality and stress prevention. The heel edge is precisely deburred using a 4 mm ball end mill, removing sharp transitions that could later initiate cracks under cyclic load. This step may appear minor, but it plays a decisive role in long-term durability, especially for gears operating under fluctuating torque and shock loads. The process then advances to finishing operations, executed in 2 distinct stages. First, the concave flank is finished using the same universal up-gear finishing cutter, followed by the convex flank. Each flank is machined independently to achieve optimal contact conditions. CNC-controlled toolpaths allow exact control of flank topology, enabling fine adjustments to load distribution, transmission error, and noise behavior. This level of precision is essential for large bevel gears, where even minimal deviations can lead to uneven load sharing and premature wear. Parallel to gear manufacturing, pinion shafts and drive shafts undergo equally rigorous processes. A typical pinion shaft with module 3.0 mm and 15 teeth is first turned to final concentricity, followed by hobbing and systematic deburring. Drive shafts with module 2.65 mm and 20 teeth follow a similar route, incorporating turning, drilling, hobbing, and edge finishing. Quick and simple tool change systems reduce setup times while maintaining repeatable accuracy across batch production. Quality assurance is not a single checkpoint, but a continuous closed-loop concept. State-of-the-art measuring centers from Klingelberg verify tooth geometry, pitch accuracy, runout, and flank deviations with micrometer precision. In addition, the physical contact pattern is evaluated and documented, confirming that load transfer occurs exactly as designed. Any deviation triggers immediate feedback to machining or grinding stages, ensuring rapid correction. To further safeguard reliability, magnetic particle testing is performed to detect surface cracks invisible to the naked eye. This non-destructive testing method provides confidence that each gear meets the highest safety standards before leaving the factory. Quality assurance remains the highest priority, especially for components destined for critical infrastructure, where failure is not an option. The process concludes with final examination and customer acceptance tests, conducted entirely in-house. Functional checks, dimensional verification, and documentation review ensure full compliance with specifications. Once approved, optimized dispatch handling by skilled specialists protects the massive components during transport, preserving precision all the way to installation. From raw steel to finished gear, this manufacturing process represents the intersection of heavy industry and ultra-precision engineering. Every operation, cutting, deburring, heat treating, grinding, and inspection, adds measurable value. The result is a colossal gear capable of operating quietly, efficiently, and reliably under extreme loads, proving that even the largest mechanical components are ultimately defined by precision measured in microns. When gear manufacturing reaches extreme industrial scale, the technology behind it becomes a fusion of advanced metallurgy, heavy machining, and precision control. A gear with a diameter of 17.5 meters represents the upper limit of mechanical engineering and is typically reserved for applications where enormous torque must be transmitted continuously and reliably. The manufacturing process starts with carefully selected alloy steel engineered for high strength, fatigue resistance, and long service life. For gears of this magnitude, the blank is usually cast or forged under controlled conditions to ensure structural uniformity and minimal internal stress. In many cases, the gear is produced as a segmented ring, allowing individual sections to be machined with extreme accuracy before being assembled on site. This approach overcomes transportation limits and ensures dimensional stability across the full circumference. Gear cutting is carried out on custom-built CNC gear machining centers, capable of handling massive diameters and weights. Processes such as gear shaping or hobbing form the involute tooth profile, while rigid machine structures and low-vibration cutting systems maintain accuracy over long machining cycles. Given the scale, even minor deviations can lead to uneven load distribution, so precision is non-negotiable. Once the teeth are formed, advanced metrology systems are used to inspect pitch accuracy, tooth geometry, runout, and alignment. Laser measurement and contact probes verify that each tooth meets strict tolerances. Gears of this size are widely used in the mining industry in the United States, particularly in large open-pit mining operations. They are critical components in equipment, such as bucket wheel excavators, large grinding mills, rotary crushers, and material handling systems, where continuous operation under extreme loads is required. In these environments, failure is not an option. Downtime can cost millions. Ultimately, a 17.5-meter gear stands as a testament to modern industrial capability, combining scale, precision, and durability to power some of the largest machines operating in American mining today. With more than 64 years of manufacturing heritage, Samyang Valve stands as one of South Korea's most established producers of large-diameter industrial valves. Each finished valve reflects a carefully sequenced manufacturing workflow in which material science, dimensional accuracy, and operational reliability are treated as equally critical objectives. Although valve sizes, pressure ratings, and applications vary, the underlying production logic remains consistent across all product families. Manufacturing starts with sand mold preparation, a foundational step in large valve casting. A specially formulated molding sand is selected for its ability to compact densely, retain shape under load, and harden progressively over time. The sand is rammed tightly to form the lower mold, which defines the external geometry of the valve body. Afterward, the upper mold is prepared and aligned precisely with the lower section. Together, these two halves create a closed cavity that mirrors the final valve shape. Integrated into the mold are engineered channels for molten metal flow, including gates, risers, and gas vents. Risers are especially important, as molten steel contracts during solidification. These reservoirs provide additional metal to compensate for shrinkage and prevent internal cavities or structural weakness. Before pouring, the mold surfaces are carefully trimmed, smoothed, and coated with a refractory layer. This coating serves as a protective interface between the molten steel and the sand. Direct contact with high-temperature metal could cause sand fusion, surface erosion, or metal penetration, all of which would degrade surface finish and dimensional accuracy. The coating also improves casting release during demolding and contributes to consistent surface quality across large and complex valve bodies. To create internal flow paths and cavities, Sand cores are installed within the mold. These cores define the internal geometry of the valve, such as the flow channel, seat housing, and internal chambers. Once the metal solidifies, the cores are removed, leaving hollow spaces essential to valve function. The precision of the core directly determines internal dimensional accuracy. Core positioning systems and sealing compounds ensure that molten metal does not leak into unintended areas during pouring, functioning similarly to a gasket that prevents metal intrusion. Parallel to mold preparation, molten metal production is carried out in the foundry. Scrap steel is melted in controlled furnaces, forming the base material for the valve body. Alloying elements such as silicon and manganese are introduced to fine-tune mechanical properties, including strength, toughness, and wear resistance. Additional material is added as needed to achieve the required melt volume. Temperature monitoring is continuous, as pouring at the correct thermal window is essential for proper mold filling and metallurgical quality. Slag and impurities are removed from the melt surface to ensure cleanliness and homogeneity. Once the metal reaches its target composition and temperature, it is transferred into mobile ladles and poured into the prepared sand molds. The molten steel flows through the gating system, filling the cavity and risers completely. Sufficient metal volume is maintained to ensure that shrinkage during cooling does not compromise structural integrity. Given the mass and thickness of large valve castings, controlled slow cooling is essential. Cooling occurs over several hours, allowing internal stresses to dissipate gradually and ensuring a stable microstructure. After cooling, demolding takes place. The sand mold is mechanically broken apart, revealing the raw valve casting. Excess sand is collected, crushed, and recycled for future mold production, supporting efficient material use and reducing waste. At this stage, the casting retains visible remnants of risers, gates, and parting lines, which are removed through cutting and grinding. This stage is comparable to trimming excess material from a molded product, ensuring a clean outline before precision machining begins. The valve body then proceeds to machining operations, where dimensional accuracy and functional interfaces are established. While casting defines the overall form, machining ensures precise tolerances for flanges, sealing surfaces, and internal interfaces. CNC machining centers perform milling, drilling, and boring operations with high repeatability. Cooling fluids are typically used to manage friction heat and prevent thermal distortion of both tooling and workpiece. Accurate machining is essential for ensuring leak-free connections, proper alignment during installation, and long-term operational reliability. During machining, critical features such as bolt holes, sealing faces, and internal passages are produced to exact specifications. Tool changes and setup adjustments are performed to accommodate different valve sizes and configurations. Each machine's surface is inspected to confirm compliance with dimensional requirements, as even minor deviations could affect sealing performance under pressure. After mechanical verification, the valve undergoes surface preparation and coating. An initial primer layer, commonly red, is applied primarily for corrosion protection. This coating shields the steel body from moisture, oxidation, and environmental exposure during storage and service. A final top coat is then applied, often using color coding to identify application type. For example, red typically indicates fire protection systems, blue is used for water supply, silver for steam service, and other colors for specialized industrial uses. This visual differentiation simplifies identification during installation and maintenance. Despite differences in size, pressure rating, and application, every valve produced follows this disciplined and repeatable workflow. This comprehensive process reflects decades of accumulated experience, continuous improvement, and a commitment to manufacturing excellence in large-scale valve production. Following machining, the valve enters the assembly and functional testing phase. Internal components are installed, and the valve is subjected to repeated opening and closing cycles. Pressure is applied to evaluate sealing integrity and operational smoothness. To visually detect leaks, soapy water is applied to joints and sealing areas. The appearance of bubbles would indicate leakage, while a clear surface confirms acceptable performance. Only valves that pass these inspections proceed to the next stage. Additional tests may be conducted depending on service conditions, including pressure class or application-specific requirements. Throughout the manufacturing facility, dust collection and filtration systems are employed to maintain a clean working environment. Grinding and machining generate fine particulate matter, which is captured using water-based filtration systems. These systems protect workers, preserve equipment accuracy, and prevent corrosion of sensitive inspection tools and cameras. As one of the most critical assemblies in rail vehicles, the wheelset directly determines safety, ride quality, and long-term operational efficiency. Wheelset Integrated Service delivers a comprehensive end-to-end lifecycle solution designed to maximize reliability, safety, and asset value. The process begins with wheelset check-in and a detailed assessment of actual operating conditions, forming the basis for an accurate condition-based maintenance cycle plan. Full digital traceability of components ensures complete transparency throughout the service life. Following wheelset disassembly, the axle undergoes precision reprofiling, supported by automated thermal spray repair to restore worn surfaces. A rigorous axle integrity assessment and recertification process returns the component to as-new status. At the same time, critical components are optimized by design, and the best gearbox overhaul procedures are defined and validated through gearbox rotation testing. The wheelset is then reassembled to its original configuration, followed by automated final inspection and certification. FPM Group delivers turnkey hot forging plants designed for high-performance forging of brass, aluminum, and steel, covering the entire production chain from raw material preparation to finished components. Each plant is engineered as an integrated system, ensuring process stability, repeatability, and long-term productivity across a wide range of industrial applications. Production begins with bar sawing systems that provide precise billet cutting, followed by graphitizing machines that apply controlled lubrication to reduce die wear and improve material flow. Billet heating furnaces ensure uniform temperature distribution, a critical factor for consistent deformation behavior during forging. Forming operations are carried out using mechanical forging presses and friction screw presses, selected according to material type, part geometry, and required forming energy. To maximize efficiency, FPM Group implements full automation and supervision systems, enabling synchronized material handling, real-time process monitoring, and optimized cycle times. Post-forging operations are supported by trimming, sandblasting, and surface finishing machines, delivering components that meet strict dimensional and surface quality requirements. Heavy-duty bolt manufacturing is a highly specialized industrial process that demands extreme precision, powerful machinery, and rigorous quality control to produce fasteners capable of operating under massive loads and harsh environments. The process begins with the selection of high-strength alloy steel, typically enriched with chromium, molybdenum, or nickel to achieve superior tensile strength and impact toughness. The raw material is automatically cut into blanks and then transferred to multi-stage hot forging presses, where bolt heads are formed under forces reaching hundreds or even thousands of tons. This forming stage preserves continuous metal grain flow, significantly improving load-bearing capacity and fatigue resistance. The bolt body and head are machined to shape using high-capacity CNC machines. CNC machining ensures exceptional dimensional accuracy, concentricity, and surface quality, especially for large diameter or special geometry bolts used in critical applications. Unlike cutting, thread rolling forms the threads by plastically deforming the material under high pressure. This process compresses and strengthens the metal grain structure along the thread profile, significantly improving fatigue life, shear strength, and resistance to cracking under cyclic loads. Hydraulic control ensures consistent pitch, flank angle, and thread depth across every component. Final automated inspections measure dimensions, verify thread integrity, and perform tensile and load testing on sampled components. Through advanced machinery, automation, and strict quality control, modern bolt manufacturing delivers reliable, high-performance fasteners essential for construction, infrastructure, energy, and heavy industry worldwide. Behind massive infrastructure projects, unseen components quietly carry enormous responsibility. An anchor bolt may look simple, but its strength, precision, and durability are the result of a tightly controlled manufacturing process where every step matters. The process begins with cutting round steel bar to length using heavy-duty Peddinghouse shears, which shear the steel cleanly rather than sawing. Larger or longer bars are cut with band saws. Next, a hex head is hot forged onto one end of the bar. Induction heating raises the steel temperature to approximately 2000 degrees Fahrenheit, after which a national upsetter forges the heated end into the hex shape. Threads are cut using Landis threading machines, with cutting oil applied to control heat and ensure dimensional accuracy. Threads are inspected using gauges to verify tolerance compliance. Prior to galvanizing, bolts undergo pickling, including caustic cleaning, acid descaling, rinsing, and fluxing to prepare the surface. Hot dip galvanizing follows, immersing the bolts in 840 degrees Fahrenheit molten zinc. Excess zinc is removed by centrifuging, then bolts are quenched, inspected, marked with grade paint, palletized, and shipped with full certification documentation. Bolt manufacturing is a precision-driven industrial process that combines powerful machinery with tightly controlled production steps to deliver fasteners capable of withstanding extreme loads and long-term service conditions. Production typically begins with steel wire or bar stock feeding systems, where raw material is straightened and cut to precise lengths by automated cutting machines. These blanks are transferred into cold heading, depending on bolt size and strength requirements. High-capacity presses shape the bolt head in multiple forming stages, ensuring consistent geometry while preserving the metal's internal grain flow for superior mechanical performance. Finally, automated inspection verify dimensions, thread integrity, and surface quality before packaging. Optical measurement systems and mechanical gauges ensure compliance with international standards. Thread formation is carried out using thread rolling machines, which form threads through plastic deformation rather than material removal. This method produces smoother thread profiles, higher fatigue resistance, and improved dimensional accuracy. CNC-controlled rolling systems allow rapid adjustment for different thread standards and diameters. Through advanced machinery, automation, and strict quality control, modern bolt manufacturing delivers reliable, high-performance fasteners essential for construction, infrastructure, energy, and heavy industry worldwide. For high-strength applications, bolts pass through controlled heat treatment furnaces, where hardness and tensile properties are precisely tailored. Continuous furnaces and automated quenching systems ensure uniform metallurgical structure across large production batches. At ThyssenKrupp Steel, warm flow forming enables the production of high-precision automotive components that are up to 50% lighter than welded or cast alternatives. The technology combines controlled heating with flow forming to shape rotationally symmetric parts from sheet or tubular preforms. During processing, the workpiece is set in rotation and locally formed by rollers, forcing the material to flow axially along the tool geometry. The result is thinner, stronger components with superior surface quality, high dimensional accuracy, and excellent load-bearing performance, particularly for wheels and drivetrain applications. Plate rolling on FACS and roller machines represents a core forming process for producing large-diameter cylindrical and conical components with high-dimensional accuracy. Using advanced multi-roll technology, FACS and plate rolling systems are engineered to handle steel plates up to 120 mm in thickness and 3,000 mm in width, enabling the fabrication of heavy-duty shells for pressure vessels, energy infrastructure, offshore structures, and large industrial tanks. The rolling operation applies precisely controlled bending forces through synchronized rollers, allowing thick plates to be progressively curved without inducing excessive internal stress or surface defects. A minimum achievable diameter of 400 mm ensures flexibility for both large and relatively compact cylindrical geometries. Throughout the process, material alignment and curvature are continuously monitored, resulting in uniform roundness and consistent wall thickness along the entire length of the workpiece. This capability significantly reduces downstream welding corrections, improves structural integrity, and shortens production cycles. FACS and rolling technology therefore delivers both high-forming precision and substantial efficiency gains for heavy steel fabrication projects. Before sparks fly and steel begins to curve, everything depends on control, alignment, and absolute precision. Inside a spiral pipe mill, production begins with disciplined handling and tightly managed parameters. A forklift delivers the slit steel coil to the mandrel, where the operator secures it under controlled tension to ensure stable feeding. Once locked in place, the coil is guided into the feeder system and carefully aligned with the forming head. This alignment stage is critical, as even minor deviation can compromise spiral geometry and weld integrity. As the line engages, the steel strip enters the forming head and is continuously wrapped into a helical profile. In seconds, flat steel becomes a perfectly round spiral pipe, formed at a constant angle that defines diameter and wall uniformity. The Spiral Helix 3600 tube former maintains consistent pressure and synchronized feed speed, delivering a smooth, repeatable pipe structure. Laser measurement systems track pipe length in real time. When the programmed dimension is reached, the cutting unit activates automatically, producing a clean, precise cut without stopping the line. The finished spiral pipe exits ready for inspection, coating, or transport, proof that controlled automation turns raw steel into infrastructure at industrial scale. At the heart of TVP Steel Pipe's manufacturing facility, a fully integrated production line transforms raw steel coils into finished cylindrical steel pipes with speed, precision, and consistency. The process begins as heavy steel coils arrive on site and are inspected for thickness, width, and surface quality. Each coil is then loaded onto the uncoiler, where controlled feeding ensures stable tension before forming begins. The steel strip passes through a series of forming rollers that gradually bend the flat material into a perfectly round tubular shape. This progressive cold forming process minimizes internal stress while maintaining dimensional accuracy. Once the edges meet, high-frequency electric resistance welding is applied to fuse the seam into a continuous high-strength weld. Advanced welding controls regulate heat input and pressure, ensuring uniform penetration and structural integrity along the entire length of the pipe. Next, the pipes are cut to specified lengths, using high-speed flying saws synchronized with line speed. Each finished pipe undergoes final dimensional checks before being transferred to the stacking area. Here, pipes are aligned uniformly, stacked in precise bundles, and securely bound with steel straps to prevent movement or damage during handling. The packaged bundles are then loaded onto trucks using forklifts or overhead cranes, ready for transport to construction sites, industrial projects, or distribution centers. This streamlined end-to-end production flow allows TVP steel pipe to deliver high-volume output with consistent quality, reduced waste, and reliable delivery timelines. The result is a steel pipe solution engineered for strength, efficiency, and modern infrastructure demands. At the IFDA lock, the process of lubricating and installing the new lifting chains was carried out under strict technical and safety requirements to restore full operation of this critical inland waterway. After transportation to the site, each chain was subjected to dimensional checks, material verification, and surface inspection before integration into the lifting system. The chain assembly follows the multi-link plate Galze principle, a mechanical concept originally attributed to Leonardo da Vinci. Instead of conventional single-link chains, this design uses multiple parallel link plates, allowing more uniform load distribution across the entire chain cross-section. A key advantage of this configuration is improved lubrication behavior. Grease can spread evenly between the numerous plates and contact surfaces, significantly reducing friction, localized wear, and fatigue under high cyclic loads. Each lifting chain installed at IFD consists of 229 links and 832 link plates. The material provides a minimum tensile strength of 200 N per square millimeter, while the calculated braking load reaches 200 kilonewtons, ensuring a high safety margin for lifting the massive lock gates. The length of each chain is 510 millimeters, and the system operates with 4 chains working in parallel to ensure balanced lifting forces and redundancy. Before commissioning, the chains were thoroughly lubricated, precisely aligned, and gradually tensioned within the lifting mechanism. Controlled load tests confirmed correct force distribution and smooth operation. Once installed, the new chain system successfully restored reliable lock operation, re-establishing safe and uninterrupted navigation along this important waterway corridor, while significantly improving long-term durability and operational security. A hydraulic open-die forging press shapes large metal components through controlled compressive force between flat or contoured dies. The process allows precise grain flow control, high structural integrity, and flexibility for oversized parts, making it essential for heavy industry, energy, and high-load mechanical applications. A bolt and nut manufacturing machine is the core equipment in modern fastener production, designed to deliver high output while maintaining strict dimensional and mechanical accuracy. Built for continuous industrial operation, this machine integrates multiple forming and finishing functions into a single, highly automated system. These blanks are fed into a multi-station cold forging machine, where powerful mechanical presses form the bolt head or nut body in a sequence of controlled steps. Each station performs a specific operation, allowing complex geometries to be produced at high speed with exceptional repeatability. Thread formation is carried out by dedicated thread rolling machines. Using hardened rolling dies, threads are formed by plastic deformation, producing smooth, dense threads with superior fatigue resistance compared to cut threads. The machines automatically adjust pressure and alignment to ensure uniform thread depth and pitch. Modern bolt and nut machines are equipped with PLC control systems, servo-driven feeders, and real-time sensors that monitor forming force, tool wear, and cycle stability. Automatic lubrication and quick change tooling minimize downtime and extend machine life. Optional inline heat treatment and surface finishing modules can be integrated to meet strength and corrosion resistance requirements. With high-speed, precision control, and robust construction, bolt and nut manufacturing machines are engineered to produce millions of fasteners reliably, supporting large-scale industrial, construction, and infrastructure projects. Gears are among the oldest mechanical components ever developed, yet they remain fundamental to modern engineering, from wristwatches to aerospace propulsion systems. At their core, gears are toothed mechanical elements designed to transmit torque, speed, and motion between rotating shafts with high precision and reliability. Their geometry, material, and manufacturing method directly determine efficiency, noise behavior, load capacity, and service life. Several gear types dominate industrial applications. Spur gears, with straight teeth, offer efficient power transmission and are widely used where simplicity and accuracy are required. Helical gears feature angled teeth that engage gradually, reducing noise and vibration, making them ideal for automotive transmissions. Bevel gears transfer motion between intersecting shafts and are critical in differentials and power tools. Manufacturing methods are selected based on gear size, complexity, material, and production volume. Casting allows the production of large gears with complex shapes, though with moderate accuracy. Forging produces gears with superior strength and fatigue resistance by refining the metal's grain structure. Powder metallurgy enables near-net shape gears with excellent dimensional consistency, particularly for high-volume production, though size and load capacity are limited. Extrusion is typically used for gears with uniform cross-sections, such as racks. For high-precision applications, machining remains essential. Processes such as hobbing, shaping, broaching, and milling generate accurate tooth profiles and tight tolerances. Machining is often combined with heat treatment and grinding to achieve optimal surface hardness, geometry, and durability. Across automotive, aerospace, robotics, manufacturing, and consumer products, gear manufacturing delivers one critical value: controlled, efficient, and reliable motion, powering modern technology at every scale.